I wish to thank the organizers for giving me this opportunity to speak on work I have done on this problem. This in published a few months ago. When I came across the properties of sodium hexaboride, ytterbium boron 12, discovered by Suchitra Sebastian and Dr. Lee, that is the Dihaston-Alphen experiments, as well as the specific heat and what played a prominent role in my thinking in these materials, which I know in the region that the Dihaston-Alphen oscillations are observed, I understood that some new kinds of particles were required to understand these experiments. This was not convenient. At the same time, a paper appeared by Bhaskaran, which uh, earlier results of Erten et al. And then the paper appeared by Arten, pointed out if propagating Majoranas exist in insulators, they will exhibit the Huston-Alphen oscillation. But I couldn't understand the thought of the Majoranas in these insulators. There was some talk about two-channel DC, and some talk about superconductivity, none of which I understood. And I set about to understand why Majoranas exist in such materials. This followed the fact to go on the mixed valence impurity and realized that it is different from a Kondo impurity, and with some collaboration, discovered zero energy, low energy singularities in the mixed valence problem, which are of course absent in the Kondo problem. And what I have in this paper is to show that these results can be expressed in terms of a localized Majorana and a propagating Majorana, and an extension to a lattice of mixed valence ions. And I have some other properties I can talk about as predictions. What's the difference between a Kondo impurity and a mixed valence impurity? As is very well described by the Anderson model, which has particle-hole symmetry, potential for localized, strongly correlated levels. The charge changes from one charge to the next at discrete intervals of energy, often called U, and chemical potential, everything is fine, and that's the Anderson model, which is all get model the properties of the Kondo impurity, which are completely analytic at low energy. Valence impurity is different, and this was discovered in the first paper written on these problems by January 6th, that two charged states are close to the chemical within an energy of the hybridization rate, gamma. Then the for charge fluctuations are important. The fact that there are two discrete charge states means both states have to obey the Friedel sum rule. That's essential. Without obeying the Friedel sum rule, the in a realistic system would be infinite. Now, the one parameter U of the Anderson model cannot force Friedel sum rule parameter. This was pointed out to me by Phil Anderson around about the same time. If you read the acknowledgement in Duncan Haldane's paper, it was pointed out to Duncan a mean field calculation, and he found that there was a first order phase transition at the mixed valence point when things become in this fashion. Now, actually, the problem is a lot more interesting than that. Discover a Wilson renormalization group solution by Elias Perakis and Andrei Rukenstein, and analytically investigated by Bosonization to discover that there are low energy in Andrei Rukenstein and me. And what I'm going to do is to show you that this solution, the singularities, here you see the charge susceptibility is calculated as the critical value for mixed valence. It's a log-log scale, so there's indeed enormous change. Also, this paper, Ijimachi, we discovered omega over t singularities of magnetic excitation, and these are essential R and mu-SR relaxation rates as discovered in samarium hexaboride and ioxyron 12. So there are low energy singularities, and to have Majoranas in a problem, you need low energies. So the model that to be investigated is a model of I'm first talking about the impurity model, a local Hamiltonian H0 plus the kinetic energy, but the kinetic energy of two channels of electrons, one we call the hybridizing channel and another called the signal, and these have to be orthogonal. And the local model, besides having these three terms, model has a new parameter V, which is tuned to adjust to have Friedel sum rule being satisfied. Now, the way to analytically go to the limit, the strong coupling limit, where U and V are much larger than all the kinetic energies in the problems, lowest energy eigenstates. And these eigenstates can be listed by, can be labeled by the screening channel. So there's a state in which you have plus in the hybridizing channel with spin up, sigma, with 0 electrons in the screen. Another many body or excitonic state in which there is no charge in the hybridizing channel, but charge in the channel, and that has another energy, and these two must satisfy the point. The important fluctuations are really fluctuations between the states eta and the states which is both charge and spin fluctuations. After a sequence of unitary transformations, which I will not describe, the Hamiltonian can be expressed of spinless fermions. The Hamiltonian is a local Hamiltonian we'll describe fermion, which reside in, let's say, Wilson orbitals around different sites. And the Hamiltonian is expressed in terms of the occupation number of 3 different fermions. One of them is the fermion, which is the same fermion which is transported away by the kinetic energy. And then there are 2 other fermions. It turns out that this local Hamiltonian be expressed as, when you diagonalize it, it is a sum of 2 Hamiltonians on the even basis, meaning that N0 plus N1 plus N2 is even, and N0 plus N2 is odd. And you discover that for a particular choice of parameters, meaning the mixed value, these it's a supersymmetric. What do I mean? I mean that for this choice, the parameter, the four states of the even basis and the four states of the odd basis general. So if you regard the even states as supersymmetric Hamiltonian, and the most interesting property, the operator zero is real in these eigenstates. So it's a Majorana. What do I mean by that? I mean that if you take of C0 acting on to the right by the object, which is the ground state in the odd channel, and on the left by the eigenstate of the ground state of the even channel, the number and real number as we do with the C0 acting on the right, left, and this is the definition of an operator being real. And if it's real, you can, in terms of sum of two ordinary fermions, is that the conjugate Majorana, I A0 minus A0 dagger square matrix element 0. Given this, including the kinetic energy, the problem can be analyzed, and you are left with a localized Majorana, which is this object, and the propagating hybridized Majorana, the ground state entropy of half R log 2. And the important point is that this C0 is real also for matrix elements to excited states, and C0 also between ground and excited states. And this is essential for the extension lattice that I'm going to do, because I generate through excitations or virtual excitations connection between this Majorana and different sides. Now, there's an approximate generalization to the lattice that one can do now, and for that, Valence singularities, you do not need fine-tuning. This is as long as you're in the middle, you will have this problem expressed in this term. So it has the kinetic energy, which is propagating Majoranas of C and C bars with some dispersion in EK. And then you have the local state goes from odd to even or even to odd fermion C, and C bar is not involved. So the spectrum just, and the spectrum of C becomes a gap spectrum, well-known mixed valence kind. And now, using the argument of Bhaskaran, the free Majorana will give magneto oscillations. So some predictions from this, and this is important to verify, and perhaps Dr. Singh will speak about it. There is no spin splitting effects in the Haas-van oscillations, which you can feel it, and that the ground state entropy, or at least till some very low takes down, and the whole phenomena, including the magneto oscillations, would then cease. Till that point, very low energy singularity in the specific heat, so that point in temperature, you will see entropy. So what's exciting about this is that for the single impurity is mixed valence impurity, is absolutely true, verified by, and there's an approximate extension to the lattice. I've not quite figured out when this kind of things will break uh, this down, but my suspicion is that at some low temperature, they will couple C and C bars, and this will cease. But till then, yeah, these predictions to vary. Thank you very much.